Imagine a substance, where just 1 gram, could create an explosion more powerful than the Hiroshima bomb. A substance that is extremely difficult to store, and costs tens of trillions of dollars to produce. A substance that could one day revolutionize space travel. Antimatter. If you haven't subscribed to our channel yet, press the subscribe button now, and activate the notification bell, so you don't miss our future videos. Our universe, and everything in it, is made of atoms. The size of an atom is usually just a few tenths of a nanometer. At the center of the atom is an extremely dense nucleus, made of positively charged protons, and neutral neutrons, holding almost all of the atom's mass. Negatively charged electrons exist in a region called the electron cloud around the nucleus, and their behavior is explained by the strange laws of the quantum world, not simple planetary motion. The strong nuclear force holds protons and neutrons together, and changes in the structure of the nucleus can release enormous amounts of energy. Electricity can also be generated from these nuclear changes, such as producing electricity from uranium. If you haven't watched the video about generating electricity using uranium, I highly recommend checking it out. Scientists understand much about the structure and behavior of antimatter, but they still do not know exactly why, after the Big Bang, almost all antimatter disappeared, and the universe today is made mostly of matter. Simply put, antimatter has almost the same structure as ordinary matter, but its particles have opposite electric charges, and some opposite quantum properties. Ordinary matter. Antimatter. Electron. Positron. Proton. Antiproton. Neutron. Antineutron. Hydrogen. Antihydrogen. Although the neutron has no electric charge, the antineutron is made of antiquarks, and is fundamentally different from a normal neutron. So, how was antimatter discovered? The story goes back to 1928. When Paul Dirac, a young English physicist, was solving an equation to describe the motion of electrons traveling near the speed of light. His equation had 2 solutions, one with positive energy, and another with negative energy. Most scientists at the time considered the second solution just a mathematical mistake, or a meaningless concept. But Dirac suggested that it could represent a real particle, a particle exactly like the electron, but with a positive charge, later called the positron, or anti-electron. At the time, many scientists dismissed, or even mocked the idea. But in 1932, Carl David Anderson experimentally discovered the first positron, while studying cosmic rays, and proved that Dirac's prediction had been completely correct. This discovery marked the beginning of humanity's scientific understanding of antimatter. Anderson observed the trace of something with the same mass as an electron, but with a positive charge. Both scientists later received the Nobel Prize in Physics for their discoveries. Dirac in 1933. And Anderson in 1936. Scientists believe that large amounts of antimatter are produced in extremely energetic environments, such as around black holes, neutron stars, and cosmic explosions. On Earth, antimatter is also produced when cosmic rays collide with the atmosphere. There is even evidence that the energy generated in thunderstorms can create anti-electrons called positrons. Antimatter was one of the most exciting discoveries of 20th century physics. Many people think of it as a theoretical idea from another world, unaware that antimatter is actually produced every day. In addition, research on antimatter helps us better understand how the universe works. So, we know that antimatter is produced naturally, but can it also be created artificially? It may sound like science fiction, but particle accelerators do this every day. At the Large Hadron Collider in CERN, billions of particles and antiparticles can be produced every second, during high-energy collisions. You might ask, what exactly is CERN? CERN is the world's largest particle physics research center, located on the border of Switzerland and France, where scientists study the fundamental structure of matter, and the main forces of nature. One of its most important machines is a massive accelerator called the Large Hadron Collider, or LHC, a circular tunnel about 27 kilometers long. Inside this machine, protons are accelerated through vacuum tunnels to nearly the speed of light, before colliding at extremely high energies. These collisions recreate conditions similar to those just moments after the Big Bang, and allow scientists to study rare particles. This process is extremely difficult, because protons are incredibly tiny, and colliding them accurately requires very powerful magnetic fields and advanced technology. According to scientific estimates, producing just 1 gram of antimatter with today's technology would cost tens of trillions of dollars. The reason for this enormous cost is that at CERN, antimatter is produced atom by atom, using huge amounts of energy in particle accelerators, while the amount produced is extremely tiny. Scientists estimate that even if all of CERN's current power were dedicated solely to producing antimatter, creating 1 full gram could take hundreds of millions of years. Although producing antimatter is extremely difficult and expensive, what can it actually be used for? When matter and antimatter collide, almost all of their mass can be converted into energy, and this energy could have many applications. In nuclear weapons, only a small portion of mass is converted into energy. But in matter-antimatter annihilation, almost all of the mass can be transformed into energy. If just 1 gram of antimatter collided with 1 gram of matter, the resulting explosion could release roughly 3 times the energy released by the Hiroshima bomb, and cause enormous destruction. The amount of energy released is almost unimaginable. That is why antimatter is considered one of the most expensive and energetic substances humanity has ever created. This is one of the most powerful methods of energy production. Antimatter also has important medical applications. The positron, which is a type of antiparticle, is used in PET scans. This technology helps doctors diagnose diseases such as cancer more easily, and even treat them. One of the most important ideas for antimatter is using it as fuel for future space travel. In the future, antimatter may be used as spacecraft fuel, because the energy it produces could move spacecraft at speeds close to the speed of light. Now, with all these descriptions of antimatter, let's also talk about some of its disadvantages. First, producing it is extremely difficult and extremely expensive. Second, if antimatter fell into the wrong hands, it could be turned into highly destructive weapons that could threaten the lives of millions of living beings. Third, storing antimatter is extremely complicated. This means it cannot be stored in a normal container made of ordinary materials. That is why scientists use a system called a penning trap, which suspends antimatter in a vacuum, using electric and magnetic fields. Controlling antimatter is extremely difficult, because even contact with a few air molecules can instantly destroy it. For this reason, scientists still have not been able to safely and stably store large amounts of antimatter. Antimatter remains one of the most mysterious parts of modern physics, a substance that could both change the future of space travel and release the most dangerous energy imaginable. Perhaps the answer to why the universe is made of matter is hidden within antimatter itself. And with that, we've reached the end of today's video. We hope you found this video interesting. Write your thoughts in the comments below. Thank you for watching, and don't forget to subscribe and activate the notification bell, so you never miss our future videos. Goodbye.